I'm here today with Lee Starkle, who's in charge of this amazing machine that makes power. It's a cogeneration plant. So your job is to oversee and make sure this rascal runs?
Yes.
It's very interesting.
Yes.
It's an honor to be here. So to put this boiler in, I understand you weren't here when they put it in, but what kind of decision process did they have to go through? What was the process to decide to do this?
Well, the existing boilers they had was for dry and lumber only, and they were 1908 manufacture date, so for before welding, so they're riveted. So for obvious reasons, insurance company says that we're not going to insure these things anymore. Had to make a decision to upgrade. You know, that's what you do when you keep the business running, is you improve your equipment. So at the time they thought, well, we could put in a small boiler and dry lumber, or we could try to match our fuel output from the mill and put in a bigger boiler and make power and have some revenue. So that's what they decided to do.
Smart move.
Yes.
I'm glad to see it. So my purpose here today is to understand the whole process, because one of the waste products you have is char, and we can put that in the ground and use that in agriculture. So I'm really excited to see how you do this, and also excited to see the lab test to see what that char contains, so we can put it to work in agriculture in the Flathead Valley and maybe other places.
Great.
So it's a good thing.
Using our waste to putting it to good use. We're fully committed to helping you do that.
All right, it's good.
So this boiler is controlled by PLC control, programmable logic control. All the valves, dampers, fans, motors, everything is started and controlled from a computer. Main screen we watch, this controls the boiler, the water, the ash, the fuel. Over here we have controls for the hot fuel handling system. We have a Wellens boiler, and this part down here is the fuel cell or the furnace, the hog fuel, which consists of the mill lumber when they debark the trees, and outside post and pole, and they will grind, wood grinds some of the fuel from the logging out in the woods. It's a mixture of that, about 40% moisture content. About 200 tons a day comes down the chute, and it lands in a little pyramid pile down here on the grates. To have combustion air blowing in underneath the grates, and we have overfire air coming through these twir holes. The overfire air helps with efficiency. It's approximately 1,500 degrees inside the furnace, and the boiler sits up on top of there. From empty to normal operating water level, the boiler holds about 3,500 gallons of water. So the heat, the gases of combustion are traveling from the furnace into the superheater wall, then the second wall, third wall, out the back. Kind of drew some particulate, which is ash, unburned fuel, and that particulate is carrying through the boiler. 1,500 degrees here on the boiler out, we're about 600 degrees. We utilize that heat that's going to go out the stack. So we put in an economizer, which is a tube shell heat exchanger to preheat the feed water, make us more efficient. And then it goes to an air heater, which is a tube shell heat exchanger. It's preheating the combustion air for combustion. So we're putting hot air in instead of cold air. And there's a drop out under the air heater that drops ash out. And then the flue gas continues on to the multi-cone, which is a mechanical collector, separates the particulate from the flue gases. So it also has another dropout, dropping out ash. And the ID fan, induced draft fan, is pulling a negative draft, negative 0.5 here, and it's pulling this draft all the way through the equipment, through the fan. Then it's a positive pressure on the outlet of it to the ESP, electrostatic precipitator. And this is got electrical current in there, and it zaps the particulate, ionizes them, magnetizes them, sticks to plates and little wrappers, knock the ash down. The remaining ash drops out. All that ash is carried in a conveyor to a bunker, where we end up with about 8 tons a day is the average of ash by feeding in 200 tons a day of fuel. Yeah, so this is what we call the fly ash, and there's also ash coming from the undergrate, which is sand and rock and and a little bit of ash. When these grates roll, they'll roll for 30 seconds every 5 minutes or whatever the operator has it set at. It'll drop that ash down into this conveyor, and this conveyor hauls it up to another bunker. The steam, we're boiling this water, we're bringing it up to pressure to 650 psi, 725 degrees superheated temperature. And the steam comes out of the boiler, goes to the turbine. Steam hits the turbine and spins it, kind of like wind on a windmill. We spin that turbine at 5,500 RPMs. And as that steam's losing its energy, we extract out 50 psi steam for the dry kilns to dry lumber and sawmill building heat. So that's why we're cogeneration. We're using the steam twice. There's a 3-to-1 ratio gearbox. The generator is making 12,470 volts at 172 amps and spin at 1,800 RPMs. And the average home in Flathead uses about 842 kilowatts per month. So 3 megawatts would be powering about 2,375 homes. Everybody always asks, what's a generator? How does the generator work? A generator is the opposite of a motor. A motor, you give it amps and it gives you torque. We give the generator torque and it gives us amps. So when we get to 5,500 RPM on the turbine, we will sync the generator with the utility, which means we're matching the voltage and the frequency. And once our breaker closed and we're connected to the utility, the strong magnets of the utility will keep that generator running at 1,800 RPMs. Even if we were to shut the steam off, it's still going to be spinning. So we open the high pressure valve and increase the steam going to the turbine to increase the torque. It's trying to speed up the turbine, but it's not, because we're connected to that utility. So it adds torque to the turbine, to the gearbox. We start adding torque to the generator, and the more torque we add, the more power we make. So the steam is pure and the minerals will stay in the boiler, in the water. So the condensate is perfect feed water because it doesn't have any minerals in it. It's got really low conductivity, mineral free. So the 10 gallons a minute of makeup water, we run through a water softener, multimedia filter, and a reverse osmosis to take the minerals out, but it's still not as good as the condensate return. So the mixture of the 3 condensates and the makeup water feeds back into the boiler, and it's just a continual cycle of reusing the water. So the usable char is coming out of the first 2 dropouts.